What if I told you that everything we can see, the stars, the galaxies, even our own bodies, makes up less than 5% of the universe? The rest is an invisible, enigmatic force, lurking in the shadows of space, shaping the cosmos in ways we're only beginning to understand. This isn't science fiction, it's the reality of dark matter and dark energy, two of the most baffling mysteries in modern astrophysics. Think of the universe as a grand stage play. The actors, the planets, the stars, are just the visible performers, but behind the scenes there's an unseen director pulling strings, dictating the motion of galaxies and accelerating the expansion of space itself. That's the power of dark matter and dark energy, and yet despite decades of research, we still don't know what they truly are. Imagine holding a magnet near a pile of iron filings. You can't see the magnetic field, but you know it's there because of how the filings move. Dark matter works in a similar way. We can't see it, but its gravitational pull bends light, twists the paths of galaxies, and holds the cosmic web together. And then there's dark energy, an even more mysterious force pushing the universe apart faster and faster, as if space itself has a hidden engine. Together, these invisible giants make up roughly 95% of the universe's total mass and energy. Yet they leave no trace we can directly detect. No light, no radiation, no particles we've been able to capture. It's like trying to solve a puzzle where most of the pieces are missing. That's where this journey begins. Over the course of this video, we'll unravel 30 of the most compelling mysteries surrounding dark matter and dark energy, from the strange behavior of galaxy clusters to the mind-bending theories that attempt to explain why the universe is tearing itself apart. We'll explore cutting-edge experiments, dive into the minds of the scientists racing to decode these cosmic secrets, and even confront the possibility that our understanding of physics itself might need a radical rewrite. So buckle up. This isn't just a tour of the unknown, it's an expedition to the very edges of human knowledge, where every discovery raises new questions and every answer leads deeper into the dark. The story of dark matter begins not in the vast emptiness of space, but in a crowded room of skeptical scientists nearly a century ago. In the 1930s, a fiery astronomer named Fritz Zwicky was studying the Coma cluster, a massive gathering of galaxies millions of light years away. He noticed something bizarre. The galaxies were moving so fast that they should have flown apart long ago. According to the laws of gravity, there simply wasn't enough visible matter to hold them together. It was like watching a spinning carousel with no one pushing it. The motion made no sense. Zwicky called this invisible glue dunkel materie, or dark matter, but his peers dismissed it as wild speculation. Decades later, another astronomer, Vera Rubin, stumbled upon the same cosmic anomaly while studying spiral galaxies. She expected the stars at the edges of these galaxies to orbit slower, just like planets farther from the sun. But to her shock, they zipped around just as fast as the inner stars, as if some unseen hand was propping them up. The numbers didn't add up. If only visible matter existed, these galaxies should have torn themselves apart. Rubin's meticulous observations became the smoking gun that forced scientists to confront an uncomfortable truth. The universe is filled with something we can't see, something that doesn't interact with light but bends the very fabric of space with its gravity. This missing mass problem still haunts us today. Every galaxy we've studied dances to the same impossible tune, defying Newton's centuries-old laws unless we account for dark matter's invisible pull. Even now, when we map the cosmos, we find vast webs of dark matter, threads of gravity stretching across billions of light years, shaping where galaxies form and how they move. Yet after all this time, we still don't know what it's made of. Is it an undiscovered particle, a flaw in our understanding of gravity, or something even stranger? The mystery only deepens the more we look. But the mystery of dark matter doesn't stop with spinning galaxies. Some of the most compelling evidence comes from a cosmic phenomenon so strange, it could be ripped straight from a sci-fi novel: gravitational lensing. Picture this: light from a distant galaxy doesn't travel in a straight line to reach us. Instead, it bends around massive objects, warped by their gravity like a marble rolling across a trampoline dented by a bowling ball. But here's the catch: sometimes telescopes capture light bending around nothing. No visible matter, no galaxy cluster, just an invisible force twisting space itself. That's dark matter in action. One of the most dramatic examples is the Bullet Cluster, a cosmic collision, two galaxies plowing into each other at millions of miles per hour. When astronomers mapped it, they found something eerie. The visible matter hot gas glowing in X-rays had crashed and stalled like two cars in a wreck. But the gravitational lensing effect kept moving, as if something unseen had sailed right through the crash untouched. The only explanation: clouds of dark matter passing through ordinary matter like ghosts, leaving no trace except their gravitational shadow. If that doesn't send chills down your spine, consider this. Entire galaxies could be floating in vast halos of this invisible substance, with stars orbiting something we'll never see. And then there's the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light carries tiny temperature variations, a snapshot of the infant universe. But the patterns in that light don't make sense unless we factor in dark matter's gravity sculpting the early cosmos. Think of it like footprints in wet cement. The way those ripples froze into place tells us something massive was there, pulling matter into clumps long before stars or galaxies existed. Even more bizarre, the math says dark matter must be slow-moving, cold enough to form those structures, yet we've never caught a single particle of it. So where does that leave us? With a universe where the evidence is everywhere but the culprit remains hidden, every time we think we've cornered dark matter, whether through underground detectors, particle colliders, or space telescopes, it slips away, leaving behind only gravitational breadcrumbs. Some theories suggest it could be WIMP, weakly interacting massive particles so elusive they barely touch ordinary matter. Others propose axions, hypothetical particles lighter than a whisper. And then there's the radical idea that dark matter doesn't exist at all, that gravity itself works differently on cosmic scales, a flaw in Einstein's equations we've yet to uncover. One thing's certain: until we solve this puzzle, we're staring at a cosmos where 95% of reality is still written in invisible ink. Among the many theories attempting to crack the dark matter mystery, one candidate stands out as the most promising and the most elusive. Weakly interacting massive particles, or WIMP, are the universe's ultimate ghosts. Theorized to be heavy, sluggish particles that barely interact with normal matter, they could be the invisible architects behind the gravitational scaffolding of the cosmos. Think of them as cosmic neutrinos, but with far more mass and even less interest in making their presence known. The beauty of the WIMP hypothesis lies in its elegant symmetry. According to particle physics, the early universe was a seething soup of particles and antiparticles colliding and annihilating in a violent dance. WIMP, if they exist, would have been forged in that chaos, rare survivors of an ancient battle, left floating through space like cosmic relics. Here's the kicker: calculations suggest there should be just enough of them left to account for all the missing mass we observe. It's as if the universe handed us a receipt and the numbers match almost too perfectly. But how do you find something that refuses to interact with almost everything? WIMP, as their name suggests, would only communicate via gravity and the weak nuclear force, the same force behind radioactive decay. That means they could pass through entire planets without leaving a trace. To catch them, scientists have built some of the most sensitive detectors ever conceived. Experiments like LUX and Xenon 1T use vats of ultra-pure liquid xenon, buried deep underground to shield them from cosmic noise. the hope that a WIMP might, just once in a blue moon, bump into a xenon atom, creating a faint flash of light or a ripple of charge. So far, the results have been a mix of tantalizing near misses and crushing silence. A few experiments have reported possible signals like whispers in the dark, but none have been confirmed. The detectors grow more sophisticated every year, pushing the limits of human ingenuity, yet WIMP remain frustratingly out of reach. Some researchers wonder if we're hunting ghosts with the wrong net, that dark matter might be something even stranger, like axions or primordial black holes. Others argue we just haven't looked hard enough, that the answer is still hiding in the data, waiting for that one golden collision. The stakes couldn't be higher. If WIMP are real, they wouldn't just solve the dark matter puzzle, they'd open a window into physics beyond the standard model, rewriting our understanding of the universe's basic building blocks. But if they're not, then we're back to square one, staring into the void, forced to question whether the answers we seek are even within our grasp. Either way, the hunt continues, a high-stakes game of hide and seek with the cosmos itself. While WIMP dominate the dark matter conversation, they're far from the only suspects in this cosmic whodunit. Enter axions, particles so light and ethereal, they behave less like discrete bullets and more like ripples on a pond. Proposed in the 1970s to solve a puzzle in quantum physics, axions have since emerged as dark matter's dark horse candidate. Unlike sluggish WIMP, these hypothetical particles would be billions of times lighter, potentially flooding the universe in a ghostly wave that permeates every corner of space. Picture the difference between trying to catch a boulder rolling downhill versus a mist so fine it slips through your fingers. The appeal of axions lies in their dual purpose. They were initially dreamed up to explain why the strong nuclear force, the glue holding atomic nuclei together, obeys perfect symmetry, a problem called the strong CP problem. If axions exist, they'd elegantly resolve this while also accounting for dark matter's gravitational grip. It's like discovering a single key that unlocks two separate vaults of cosmic secrets. But detecting them is a nightmare. With negligible mass and no charge, axions would barely interact with ordinary matter. Instead, scientists hunt for their faint whispers using ultra-sensitive magnetic fields, hoping to convert them into detectable photons in experiments like ADMS. It's the equivalent of listening for a feather landing in a hurricane. Then there's the wild card, primordial black holes. These aren't the black holes formed from dying stars, but hypothetical relics from the universe's first chaotic moments, smaller than an atom yet as massive as a mountain. Imagine trillions of these microscopic monsters drifting unnoticed through space, their gravity collectively shaping galaxies. Some theories suggest they could explain dark matter without inventing new particles at all, just ancient cosmic debris we've overlooked. But there's a catch. If these black holes were too numerous, we'd see their lensing effects distorting starlight, and surveys like OGLE have found far fewer than needed to solve the mystery. The sheer diversity of candidates, WIMP, axions, black holes, even stranger ideas like sterile neutrinos, reveals how deep our uncertainty runs. Each hypothesis has its own tantalizing clues and deal-breaking flaws. WIMP fit the math beautifully but refuse to show up in detectors. Axions are elegant but frustratingly elusive. Primordial black holes are a minimalist solution, yet the evidence for them is thin. This isn't just scientific indecision, it's a sign that dark matter might be more complex than we imagined. What if the answer isn't one single culprit but a mix of these entities? Or something entirely outside current physics? The fact that we're juggling so many possibilities underscores a humbling truth. We're still decoding a universe where the rules might be stranger than fiction. Every time one door closes a failed experiment, a disproven model another cracks open, offering a glimpse into the unexplored. Whether it's WIMP, axions, or something beyond our current imagination, the hunt for dark matter isn't just about finding missing mass. It's a quest to rewrite the very definition of reality. buried deep beneath Italy's Gran Sasso mountain, shielded from cosmic interference by a mile of solid rock, an experiment has been quietly claiming the unthinkable for over 2 decades: direct detection of dark matter. The DAMA project, later upgraded to DAMA/LIBRA, uses ultra-pure sodium iodide crystals to hunt for the faintest whispers of particle collisions. But what makes this team's results so explosive and so controversial is their reported discovery of an annual signal that pulses like a cosmic heartbeat. Every June, their detectors light up slightly more. Every December, the activity dips. This rhythmic dance, they argue, is the smoking gun of dark matter flowing through Earth as we orbit through the galaxy's invisible halo. Here's why that's revolutionary if true. Our solar system isn't stationary. It's racing around the Milky Way at 200 kilometers per second. If dark matter permeates the galaxy, Earth should plow through a thicker wind of these particles in June, when our planet's motion adds to the sun's velocity, and a thinner stream in December when the motions oppose. DAMA data fits this prediction with uncanny precision, showing a modulation that aligns perfectly with astrophysical models. It's like hearing the universe's hidden soundtrack, a crescendo and decrescendo timed to our planet's yearly voyage. But the scientific community remains sharply divided. No other experiment has replicated DAMA results despite numerous attempts. Projects like LUX, Xenon, and Cosine have scrutinized the same mineral sodium iodide under even more sensitive conditions, only to find silence. Critics point to potential pitfalls: background radiation from local geology, temperature fluctuations in the underground lab, even statistical quirks that could mimic a signal. The DAMA team, however, stands firm. They've refined their methods for decades, accounting for every variable, and the signal persists. It's a stalemate that's fueled heated debates at conferences, with some researchers calling it a systematic error and others wondering if we're missing a fundamental piece of the dark matter puzzle. One tantalizing possibility: DAMA might be detecting something real, just not the dark matter we expected. Hypothetical particles called mirror matter, or strongly interacting massive particles, could produce annual modulation without being spotted by other detectors. Or perhaps dark matter interacts differently with sodium iodide than with xenon or germanium, the materials favored by rival experiments. This wouldn't just challenge our detection methods, it could upend our understanding of dark matter's very nature, suggesting a zoo of particles rather than a single culprit. The controversy underscores a deeper truth in science. Extraordinary claims demand extraordinary evidence. Until another lab confirms the signal, or DAMA results are debunked conclusively, this experiment remains a tantalizing enigma. It's a reminder that the universe's darkest secrets won't surrender easily, and that every flicker of hope must be scrutinized under the harshest light. Whether DAMA has glimpsed the shadow of dark matter or stumbled into an elaborate illusion, one thing's certain: the quest to solve this mystery is far from over. If you could step back and view the universe from beyond its edges, you'd see not random chaos but an intricate, luminous web stretching across billions of light years. Galaxies cluster along shimmering threads like beads on a string, separated by vast, empty voids darker than anything imaginable. This cosmic web, the largest structure in existence, isn't woven by stars or gas. It's sculpted by the invisible hand of dark matter, whose gravity dictates where galaxies form and how they move. The secret to this architecture lies in dark matter's unique properties. Unlike ordinary matter, it doesn't collide, radiate, or clump. Instead, it forms sprawling, diffuse halos that act as gravitational anchors. In the early universe, tiny fluctuations in dark matter's distribution, seeds planted by quantum ripples during the Big Bang, began pulling matter together. Over eons, these patches grew into a network of filaments, with galaxies forming at the densest intersections. The voids, those are the abandoned construction zones, regions where dark matter's pull was too weak to gather material. To visualize this, scientists rely on supercomputer simulations like the Millennium Run, which model dark matter's evolution from the universe's infancy to today. The results are staggering, a dynamic tapestry where dark matter flows like rivers of unseen ink, carving channels that ordinary matter simply follows. One simulation even revealed a filament spanning 500 million light-years, a bridge of gravity connecting two galactic superclusters. But here's where it gets eerie. When we compare these simulations to real galaxy surveys, the match is uncanny. The Sloan Digital Sky Survey, which mapped millions of galaxies, shows the same web-like patterns predicted by dark matter models. It's as if we've uncovered the universe's blueprint and the architect remains invisible. Without dark matter's scaffolding, galaxies would scatter like dust in the wind, and the cosmic web would collapse into formless haze. Yet mysteries linger. Why do some filaments appear underpopulated? Could dark matter's structure hint at undiscovered physics? Every thread of this web pulls us deeper into the dark, reminding us that the universe's grand design is still being decoded one gravitational shadow at a time. Computer simulations of the universe have a dirty little secret. They keep predicting galaxies that don't exist. Take the Milky Way's neighborhood, where astrophysicists expected to find hundreds of hefty satellite galaxies orbiting like loyal moons, held in place by vast halos of dark matter. But when telescopes scanned the skies, they spotted only a handful of faint, wispy companions. This glaring mismatch, dubbed the too big to fail problem, has forced scientists to confront a chilling possibility. Either our simulations are fundamentally flawed, or dark matter behaves in ways we never anticipated. The crux of the issue lies in dark matter's role as cosmic architect. Supercomputer models like Via Lactea and Elvis simulate how dark matter clumps together after the Big Bang, forming dense subhalos that should each host a visible galaxy. These halos aren't minor features, they're predicted to be monstrous, with enough gravitational pull to cradle galaxies as large as the Magellanic Clouds. Yet reality paints a sparser picture. The Milky Way's entourage includes only about 50 dwarf galaxies, most of them puny and dim. It's like expecting a grand royal court and finding just a few scattered attendants instead. One radical solution gaining traction: dark matter might not be the aloof, non-interacting substance we've assumed. Enter self-interacting dark matter, a theory where these particles occasionally collide not with ordinary matter but with each other. Picture a crowded room where most people pass through walls like ghosts, but every so often two bump shoulders. This subtle interaction could solve the too big to fail puzzle by smoothing out dark matter's distribution, preventing it from forming overly dense clumps. The result: fewer massive halos and more dispersed, faint satellites, exactly what we observe. Support for this idea comes from bizarre galaxies like NGC 1052DF2, a see-through galaxy with almost no dark matter at all. How could a galaxy lose its gravitational scaffolding? Self-interacting dark matter might have been scattered by collisions, like billiard balls knocked off course. Meanwhile, other galaxies show distorted shapes that suggest dark matter is being tugged around, something impossible if it were truly inert. Yet the debate is far from settled. Critics argue that tweaking galaxy formation physics, like accounting for supernova blasting gas out of small galaxies, could resolve the discrepancy without exotic dark matter. Others propose that many dwarf galaxies are simply too dim for current telescopes to spot, hiding in plain sight. The answer might lie in upcoming projects like the Vera Rubin Observatory, which could uncover a trove of hidden satellites. Until then, the too big to fail problem remains a cosmic paradox, a reminder that even our best models are just sketches of a universe still learning to reveal itself. In the late 1990s, two teams of astronomers made a discovery so shocking, it sent ripples through the foundations of physics. They weren't hunting for dark energy, they were trying to measure how fast the universe's expansion was slowing down. After all, gravity's pull should have been putting the brakes on the Big Bang's explosive aftermath, like a ball tossed upward, gradually losing speed. But when they studied distant supernova stellar explosions so brilliant they outshine entire galaxies, their data told a different story. The universe wasn't just expanding, it was accelerating, as if some invisible foot had stomped on the cosmic gas pedal. The key lay in Type 1, a supernova, nature's perfect cosmic yardsticks. These explosions always release the same amount of light, allowing astronomers to calculate their exact distance. By comparing how bright they appeared to how much their light had redshifted, stretched to longer wavelengths by the universe's expansion, the teams could trace how fast space was stretching over time. What they found defied all expectations. The most distant supernova, whose light had traveled billions of years to reach us, were fainter than predicted. The universe wasn't just expanding faster in the past, it was speeding up now, propelled by something we couldn't see. This revelation earned the researchers a Nobel Prize and introduced the world to dark energy, a force so bizarre it seems ripped from science fiction. Unlike dark matter, which pulls galaxies together with gravity, dark energy does the opposite. It pushes space apart. Imagine blowing up a balloon with tiny dots on its surface. As you inflate it, the dots move away from each other. Now imagine the balloon starts inflating faster on its own, and you'll grasp the unsettling effect of dark energy. It's as if empty space itself contains a latent energy growing stronger as the universe expands. The numbers are staggering. Dark energy accounts for roughly 68% of the universe's total energy budget, dwarfing both dark matter and ordinary matter. But here's the paradox. According to Einstein's equations, this repulsive gravity should stem from a cosmological constant, a fixed energy density of space. Yet when theorists calculate what that value should be using quantum physics, their predictions overshoot reality by a factor of 10 to the power of 120. It's the worst mismatch in science, a gap so vast it suggests we're missing something profound. To make matters stranger, dark energy's effects were negligible for most of cosmic history. For billions of years, gravity dominated, allowing galaxies and clusters to form. Only around 5 billion years ago, when the universe was already 2/3 its current age, did dark energy's push overcome gravity's pull, kicking off the acceleration we see today. Why now? Why this specific timing? The questions pile up faster than the answers. Some theories suggest dark energy isn't constant at all but evolves over time, a concept dubbed quintessence. Others propose that our understanding of gravity breaks down on cosmic scales, requiring a rewrite of Einstein's theory itself. One thing's certain, dark energy's discovery didn't solve a mystery, it unveiled a deeper one. We're left staring at a universe where the dominant force is also the least understood, an invisible driver steering the cosmos toward an unknown fate. Whether it's a property of space, a dynamic field, or a sign of new physics, dark energy remains the ultimate wild card in our quest to decode the universe's secrets. And with every observation, it becomes clearer. The more we learn, the more the cosmos defies our expectations. Einstein once scribbled a single Greek letter lambda, the cosmological constant, into his equations of general relativity, only to later call it his greatest blunder. At the time, he was wrestling with a stubborn fact: the universe refused to collapse under its own gravity. To balance the equations, he introduced this fudge factor, a repulsive force woven into the fabric of space itself, keeping the cosmos static. But when Edwin Hubble revealed the universe was expanding, Einstein ditched the constant, dismissing it as unnecessary. Decades later, that discarded term would come roaring back with a vengeance, not as a mistake, but as the key to dark energy. Here's the irony: the cosmological constant wasn't wrong, it was prophetic. Modern measurements show dark energy behaves exactly like Einstein's lambda, a constant energy density driving the universe's accelerated expansion. But there's a catch. When physicists calculate what this energy should be using quantum field theory, where even the vacuum of space crackles with fleeting particles, they hit a number so colossal, it would have torn the cosmos apart before atoms could form. We're talking 10 to the power of 120 times larger than observed. That's a 1 followed by 120 zeros, a discrepancy so vast, it's like predicting a tidal wave and finding only a single ripple in a teacup. This isn't just a rounding error, it's the largest mismatch between theory and observation in all of science, exposing a chasm in our understanding of reality. Quantum physics insists empty space should seethe with energy, yet the universe remains eerily calm. Some theorists argue this means we're missing a cancellation mechanism, some symmetry that almost but not perfectly zeroes out the vacuum's energy. Others propose the constant isn't constant at all, but a dynamic field that slowly decays, like a cosmic battery losing charge. Then there's the radical idea that we live in a multiverse, where universes with different lambda values sprout endlessly, and we just happen to occupy one where the number is bizarrely small. The cosmological constant conundrum cuts to the heart of physics' greatest challenge, reconciling gravity and quantum mechanics. Einstein's theory treats space as a smooth stage, while quantum physics sees it as a frenetic quantum foam. Dark energy sits at the collision point of these two worlds, a silent reminder that until we bridge that divide, the universe's deepest secrets will stay locked away. So while Einstein may have regretted lambda, today's physicists would give anything to understand why it's so impossibly tiny, and what that means for the fate of everything. What if dark energy isn't a fixed feature of space, but something far stranger, a cosmic shadow that ebbs and flows with time? This is the tantalizing premise of quintessence, a theory that dares to challenge Einstein's static cosmological constant. Picture the universe not as a balloon inflating at a steady pace, but as one whose expansion speeds up or slows down based on the push of an invisible, evolving force field. Unlike lambda, which remains unchanging, quintessence behaves more like a weather system shifting in intensity, potentially even switching from repulsive to attractive over billions of years. The idea hinges on a type of energy field called a scalar field, which fills space but can change its properties dynamically. Think of it like a cosmic dial. Turn it one way, and the field exerts negative pressure, accelerating expansion. Turn it another, and it might clump like matter, tugging the universe back together. Some models suggest quintessence could have played hide and seek throughout cosmic history, weak during the universe's infancy, then surging to dominance 5 billion years ago, just as supernova data reveals. Others propose it could eventually fade, allowing gravity to regain control. The implications are staggering. If true, the fate of the cosmos might not be an eternal cold rip, but a cycle of acceleration and crunch. Testing this requires spotting subtle fingerprints in the universe's expansion. While lambda predicts a very specific relationship between distance and redshift, the stretching of light from faraway galaxies' quintessence leaves wiggle room. Its dynamic nature would alter how fast galaxies recede over time, potentially leaving traces in the cosmic microwave background or the large-scale distribution of matter. Projects like the Dark Energy Survey and Euclid Space Telescope are hunting for these deviations, mapping millions of galaxies to see if dark energy's strength varies across space or epochs. But quintessence isn't the only challenger. Some theorists propose phantom energy, a more aggressive variant where dark energy's density increases as the universe expands, leading to a catastrophic big rip that tears apart galaxies, planets, and even atoms. Others explore K-essence, where the field's kinetic energy drives acceleration differently at various scales. Each model offers a unique set of predictions, some implying oscillating expansion, others a slow decay of dark energy's influence. The stakes: if dark energy is dynamic, it could mean our universe is just one transient phase in a grander cycle. Or it might hint at undiscovered particles or dimensions influencing space itself. Yet every alternative faces a brutal test, matching the razor-sharp precision of Lambda's predictions while explaining why the cosmological constant appears fine-tuned to such an improbable value. Whether quintessence survives this scrutiny or joins the pile of beautiful but wrong ideas, one lesson is clear: dark energy's mystery is far too deep for a single, simple answer. Picture a universe where dark energy isn't just a passive force, but something far more sinister, a shadow that grows stronger with every passing moment. This is the terrifying premise of phantom energy, a hypothetical form of dark energy so extreme, it doesn't just accelerate the expansion of the cosmos, it actively fuels its own destruction. Unlike the cosmological constant, which maintains a steady push, phantom energy's density increases as space stretches, creating a runaway feedback loop with apocalyptic consequences. The result, a cosmic doomsday known as the Big Rip, where not just galaxies but atoms, spacetime itself, are torn apart in a final, violent crescendo. The math behind this scenario is as elegant as it is horrifying. Normally, dark energy's repulsive force remains constant. Its energy density stays the same even as the universe expands. But phantom energy defies this logic. Here, the more space stretches, the more energy floods into existence, like a twisted version of compound interest. Over time, this exponential growth overwhelms every force in nature. First, galaxy clusters are wrenched apart, their gravitational bonds no match for the mounting pressure. Then, individual galaxies unravel, stars ripped from their orbits. As the acceleration crescendos, solar systems disintegrate, planets torn from their suns. And in the final moments, even atoms, the building blocks of matter, are shredded as the fundamental forces holding nuclei together falter. Spacetime itself frays at the seams, dissolving into a sea of disconnected particles. The universe doesn't just fade into cold emptiness, it's vivisected. What makes this scenario especially chilling is its timeline. Calculations suggest that if phantom energy exists, the Big Rip could occur in as little as 22 billion years, a blink of an eye on cosmic scales. Astronomers have even identified a critical threshold. If dark energy's equation of state value dips below -1, phantom energy becomes possible. Current measurements hover tantalizingly close, with results like -0.98 plus or -0.05, leaving the door slightly ajar. It's as if we're standing at the edge of a cliff, unsure if the ground beneath us is solid or about to crumble. But could this really happen? Some theorists argue that phantom energy violates fundamental energy conditions in physics, leading to paradoxes like negative kinetic energy or particles moving faster than light. Others counter that in the quantum realm, such bizarre behavior isn't just possible, it's routine. Certain string theory models even predict phantom-like fields lurking in extra dimensions. The debate rages on with no consensus in sight. Yet perhaps the most unsettling question isn't whether the Big Rip is possible, but what its existence would imply about our universe. A phantom-driven cosmos isn't just expanding, it's fundamentally unstable, teetering on the brink of self-destruction. It suggests a reality where the vacuum of space isn't benign, but actively malignant, growing more lethal with time. And if that's true, then the universe's fate isn't a slow fade to black, it's a scream ripped from the fabric of existence itself. What if the biggest secret of the cosmos isn't invisible matter, but broken physics? For decades, dark matter has been the go-to explanation for the universe's gravitational anomalies. But a small group of rebel scientists insists we've been chasing a ghost. Their alternative, that gravity itself behaves differently on cosmic scales, a theory provocatively named modified Newtonian dynamics, or MND. At its core, MND suggests that Newton's centuries-old laws, the bedrock of classical physics, need a tweak when gravity becomes incredibly weak, like at the edges of galaxies. No dark matter required, just a subtle rewrite of the rules we thought were set in stone. The idea was born in the early 1980s when physicist Mordechai Milgrom noticed something peculiar about galaxy rotation curves. Stars orbiting far from a galaxy's center should slow down, just like planets farther from the Sun. But as Vera Rubin's work showed, they maintain roughly the same speed. Milgrom's radical proposal, below a certain threshold of acceleration about 1/10 billionth of Earth's gravity, Newton's equations break down, causing gravity to fade more slowly than expected. This tiny adjustment neatly explains why stars at galactic outskirts don't behave as predicted. Suddenly, the need for dark matter's invisible scaffolding vanishes. And in some cases, MUND works shockingly well. Take dwarf galaxies, tiny, dim systems where dark matter models often struggle. MUND predicts their rotation curves with eerie precision, far better than standard cosmology. Even more striking, certain galaxies discovered after Milgrom's predictions, like the ultra-diffuse galaxy NGC 1052DF2, defy dark matter expectations but align suspiciously well with MUND. It's as if the theory anticipated cosmic oddities before telescopes even spotted them. But here's where the cracks appear. While MUND excels at galactic scales, it stumbles when confronted with the universe's grandest puzzles. Gravitational lensing, the bending of light around massive objects, demands the extra gravity of dark matter to explain distortions around galaxy clusters. MUND, in its original form, can't replicate these observations without smuggling in some unseen mass. Then there's the cosmic microwave background, whose intricate patterns require dark matter's gravitational influence in the early universe. Attempts to patch these holes with tweaked versions of MUND, like relativistic extensions such as TVS, often end up feeling like duct tape solutions, awkward and unconvincing. The debate rages on, fueled by each new discovery. When the James Webb Space Telescope revealed unexpectedly massive early galaxies, MUND supporters argued dark matter models couldn't explain their rapid formation, while critics shot back that MUND struggles with galaxy cluster collisions like the Bullet Cluster, where gravity's pull clearly resides where no visible matter exists. It's a cosmic tug-of-war between elegance and evidence, a battle that forces us to confront whether we're missing matter or misunderstanding physics itself. Either way, MUND's greatest contribution might be its defiance. By challenging the dark matter dogma, it keeps science honest, reminding us that even the most accepted theories must survive relentless scrutiny. Whether it's right, wrong, or something in between, its existence proves the universe still holds mysteries that refuse to fit neatly into our equations. And that's a revolution worth watching. In the quiet hum of supercomputer simulations and the precise flicker of telescope data, a cosmic contradiction has been growing, one that threatens to unravel our most fundamental understanding of the universe's expansion. It's called the Hubble tension, and at its core lies a simple, unsettling fact. The universe appears to be expanding at two different speeds. When scientists measure the Hubble constant, the rate at which space stretches using the ancient light of the cosmic microwave background, they get one number. But when they calculate it using nearby supernova and pulsating stars, they get another. The difference might seem small, just a few kilometers per second per megaparsec, but in cosmology, that's a glaring red flag. It's like weighing an object on two perfectly calibrated scales and getting different results every time. Either we're missing something colossal or the rules of the game have changed. The cosmic microwave background, or CMB, offers a snapshot of the infant universe, a relic from 380,000 years after the Big Bang. By analyzing its subtle temperature fluctuations, scientists can extrapolate how fast space should be expanding today. These measurements, anchored by missions like Planck, point to a Hubble constant around 67. Meanwhile, observations of nearby celestial landmarks type 1a supernova and Cepheid variable stars tell a different story. Their brightness and pulsation rates suggest expansion closer to 73. The gap persists even as instruments grow more precise, ruling out measurement errors. This isn't noise, it's a signal, a crack in the foundation of modern cosmology. So where does dark energy fit in? If the universe's expansion rate isn't adding up, perhaps dark energy isn't the static force we've assumed. Maybe it's evolved over time, growing stronger or weaker in ways that leave different fingerprints on ancient versus modern measurements. Imagine pouring syrup into a bowl and expecting it to spread evenly, only to find it clumped differently at the edges than the center. That's the kind of inconsistency we might be dealing with. Some theorists propose early dark energy, a transient surge that briefly accelerated expansion in the universe's first million years, skewing the CMB's readings. Others suggest dark energy could interact with dark matter, trading strength in a cosmic tug-of-war that alters the expansion rate locally versus globally. The stakes couldn't be higher. If the Hubble tension is real and not some systematic error, it implies that dark energy's properties are more complex than a simple cosmological constant. It could mean we're seeing the first hints of entirely new physics, a fifth force or a breakdown in Einstein's gravity on vast scales. Already, telescopes like JWST are diving into the discrepancy, scrutinizing distant galaxies for clues. Whether the answer lies in revised models, exotic dark sectors, or something beyond our current imagination, one thing's clear: the universe is whispering a secret we've yet to decode. And until we do, every measurement carries the weight of a puzzle that could redefine reality itself. The battle over dark matter's temperature might sound like a scientific squabble over semantics, but it's actually a clash of cosmic consequences. On one side, there's cold dark matter, slow, lumbering particles that clump together like syrup poured into water, forming the dense gravitational seeds for galaxies. On the other, warm dark matter, lighter, zippier particles that resist clustering, leaving behind a smoother cosmic landscape. The difference between them isn't just academic. It's the key to understanding why the universe looks the way it does, from the tiniest dwarf galaxies to the vast filaments of the cosmic web. Cold dark matter has long been the reigning champion, and for good reason. Its sluggish nature lets it collapse easily under gravity, creating the dense halos we think anchor galaxies. Simulations based on this model, like the famous Millennium Run, reproduce the universe's large-scale structure with uncanny accuracy, but there's a hitch. When we zoom in on smaller scales, cold dark matter struggles to explain why we don't see as many dwarf galaxies as predicted. These cosmic minnows should be everywhere, littering the Milky Way's outskirts like pebbles on a beach. Instead, we find a puzzling scarcity, a discrepancy that's fueled the warm dark matter rebellion. Warm dark matter offers a tantalizing fix. Imagine swapping those sluggish particles for lighter, faster ones, perhaps sterile neutrinos or hypothetical particles called axions. These speedsters would have zipped through the early universe like bullets through fog, smearing out the tiny density fluctuations that would have birthed countless dwarf galaxies. The result, a sparser galactic neighborhood matching our observations far better. Warm dark matter also neatly sidesteps the cusp core problem, where simulated galaxies show dense central dark matter clumps that real galaxies mysteriously lack. If dark matter particles were faster, they'd naturally spread out, smoothing those sharp cusps into gentler cores. But how do we test these competing visions? Enter the Lyman alpha forest, one of cosmology's most unusual diagnostic tools. When light from distant quasars travels through the cosmos, it passes through clouds of hydrogen gas, absorbing specific wavelengths and creating a forest of dark lines in the spectrum. These lines act like a cosmic barcode, encoding information about the gas distribution, and by extension, the underlying dark matter. Cold dark matter predicts a thicket of sharp, dense lines reflecting its clumpy nature. Warm dark matter, by contrast, should produce sparser, smoother absorption patterns, like diffused ink instead of sharp strokes. Early results from telescopes like Keck and the Very Large Telescope show tantalizing hints of warm dark matter's smoother signature, but the debate is far from settled. The stakes here are astronomical. Get dark matter's temperature wrong, and our entire understanding of galaxy formation could unravel. Cold dark matter's dominance isn't just a theoretical preference, it's baked into decades of research, from galaxy surveys to Big Bang nucleosynthesis. Yet the warm dark matter camp keeps finding anomalies that refuse to vanish. There's even a middle path, fuzzy dark matter, where particles are so lightweight they behave like quantum waves, creating a universe with characteristics of both models. What's clear is that dark matter's temperature isn't just a detail, it's a fundamental feature shaping the cosmos. Whether cold, warm, or something in between, the answer will rewrite our cosmic recipes, revealing not just what the universe is made of, but how it learned to build itself. Some of the emptiest places in the universe might hold the biggest clues about dark energy's grip on reality. Picture a bubble so vast it could fit thousands of galaxies, except there's almost nothing inside. These are cosmic voids, sprawling deserts of near-nothingness stretching hundreds of millions of light-years, where matter is so scarce that dark energy's repulsive push may operate unchecked. While galaxies cluster along shimmering filaments of the cosmic web, voids are the silent counterpoint regions where space itself seems to be winning its tug of war against gravity. The KBC void takes this emptiness to staggering extremes. Named after astronomers Keenan, Barger, and Cowie, this local cosmic anomaly is a spherical emptiness roughly 2 billion light-years wide, with our Milky Way sitting uncomfortably close to its edge. If standard cosmology holds true, voids this massive should be vanishingly rare statistical flukes in an otherwise evenly distributed universe. Yet the KBC void's sheer size and our precarious position within it raise eyebrow-raising questions. Are we living in a cosmic underdensity so extreme it skews our measurements of universal expansion? Could this explain why some local measurements of the Hubble constant disagree with predictions from the early universe? Here's where dark energy enters the scene. In dense galaxy clusters, gravity's pull keeps dark energy's expansionary influence in check, like a dam holding back a river. But inside voids, where matter's grip is weakest, dark energy may dominate unimpeded. Some theorists suggest voids expand faster than the surrounding universe, acting as accelerators where space stretches more aggressively. This could mean voids aren't just passive holes, they're active players in cosmic evolution, their growth subtly altering the rate at which the entire universe expands. Observational clues support this. Galaxies near void edges show peculiar velocities, as if being gently nudged outward by the void's expansion. Yet the KBC void's existence unnerves cosmologists. Standard simulations predict voids half its size at most. If such gargantuan emptiness is real, it might hint that dark energy's strength varies across space, or that our understanding of structure formation is missing a crucial piece. Even stranger, some measurements suggest our local universe is less dense than average, as if we're inside a Hubble bubble where expansion rates differ from the cosmic norm. Could this explain the infamous Hubble tension? The possibility lingers, tantalizing and unproven. What makes voids particularly fascinating is their dual role as both laboratories and anomalies. Their near-vacuum conditions let us study dark energy's purest effects, untangled from gravity's noise. Yet their sizes and distributions sometimes defy expectations, whispering that our models might need refinement. As telescopes like Euclid map void shapes and growth with unprecedented precision, we may finally learn whether these cosmic nothings are the key to understanding everything or the cracks in our cosmological framework. Either way, they remind us that in the vastness of space, emptiness speaks volumes. Deep in the heart of our galaxy, an invisible fire burns. The Milky Way's core should be a predictable place, a supermassive black hole surrounded by aging stars and swirling gas. But when astronomers pointed the Fermi Gamma-Ray Space Telescope toward this region, they detected something bizarre, a faint, diffuse glow of high-energy gamma rays, radiating far more intensely than known astrophysical sources could explain. This galactic center excess has become one of dark matter's most tantalizing clues, or its most frustrating red herring. The reason: those mysterious photons could be the death throes of dark matter particles colliding and annihilating in the galaxy's gravitational crucible, finally revealing their existence through destruction. The logic behind this hypothesis is eerily elegant. If dark matter consists of particles like WIMP, they wouldn't just pass through each other like ghosts, they might occasionally collide. And just as matter and antimatter annihilate in bursts of energy, two dark matter particles could obliterate each other upon impact, converting their mass into gamma rays. The Milky Way center, dense with dark matter's gravitational pull, would be the ideal hunting ground for these rare events. The gamma-ray excess fits this script disturbingly well. It's symmetrically distributed, peaks near the galactic center, and matches energy predictions for certain WIMP models. It's as if we've stumbled upon the cosmic equivalent of a crime scene, with gamma rays as the smoking gun, but alternative explanations lurk in the shadows. Astrophysicists have proposed that the excess could come from something far more mundane, like a previously unnoticed population of millisecond pulsars, the rapidly spinning corpses of dead stars. These celestial powerhouses beam gamma rays as they rotate, and their faint collective glow might mimic a smooth dark matter signal. Then there's cosmic ray interactions. High-energy protons slamming into gas clouds could produce similar photon bursts through complex particle physics. Even rogue emissions from the supermassive black hole Sagittarius A*, can't be ruled out entirely. The challenge is that all these scenarios require fine-tuning to match the data perfectly, leaving just enough room for doubt to keep the dark matter interpretation alive. The debate intensified when scientists noticed the gamma-ray signal isn't just confined to our galaxy. Dwarf galaxies like Reticulum II, which are thought to be drowning in dark matter, show tantalizing if faint gamma-ray hints too. Meanwhile, the Alpha Magnetic Spectrometer on the International Space Station has detected excess positrons in cosmic rays, another potential byproduct of dark matter annihilation. Yet with each new observation, the puzzle grows more complex. Some studies suggest the galactic center's gamma rays are slightly lumpy, inconsistent with dark matter's expected smooth distribution. Others argue the signal's energy spectrum doesn't quite align with popular WIMP models. It's a cosmic Rorschach test where every scientist sees a different pattern. What makes this mystery so electrifying is the stakes. If the gamma-ray excess truly is dark matter's fingerprint, it would be the first direct evidence of its particle nature, a Nobel Prize-worthy breakthrough that could unlock decades of questions. But if astrophysical sources are masking themselves as dark matter, it's a cautionary tale about how easily the cosmos can deceive us. Future telescopes like the Cherenkov Telescope Array aim to resolve this by hunting for correlated signals across multiple wavelengths, while particle colliders continue their underground pursuit of WIMP. Until then, the galactic center's eerie glow remains a beacon of possibility, a flickering hint that we might be watching dark matter vanish before our eyes, one gamma ray at a time. The cosmic microwave background should be the universe's most democratic feature, a nearly perfect snapshot of the Big Bang's afterglow, uniform in every direction. But when scientists peeled back the layers of this ancient light, they stumbled upon something unsettling. Dubbed the axis of evil, this bizarre pattern in the CMB reveals peculiar alignments that defy our expectations of cosmic isotropy. Certain temperature fluctuations seem to line up along a specific axis, as if the universe has a hidden preferred direction, a cosmic North Star that shouldn't exist according to standard cosmology. At the heart of this mystery is dark energy's potential role in breaking the universe's symmetry. the CMB's temperature variations should be randomly distributed like static on an untuned television. Instead, we find large-scale correlations that point toward an eerie alignment, almost as if space itself has a subtle grain to it, like wood. One shocking example comes from the quadrupole and octupole moments, mathematical terms describing how the CMB's temperature deviations are arranged. These patterns don't just appear random, they cluster along a shared axis that bizarrely aligns with our solar system's ecliptic plane. The odds of this happening by pure chance? Less than 1 in 1,000. Could dark energy be the culprit? Some theorists suggest its repulsive force might not act uniformly across the cosmos. If dark energy's strength varied slightly along certain directions, perhaps due to an early universe phase transition or a remnant asymmetry from the Big Bang itself, it could have imprinted these peculiar patterns on the CMB. Imagine blowing up a balloon with a weak spot. As it expands, that irregularity would stretch into a visible flaw. Similarly, if dark energy's push was slightly uneven, it might have left behind these ghostly alignments as a cosmic fingerprint. Skeptics argue the axis of evil could just be a statistical mirage, an illusion created by foreground contamination from our galaxy's dust or subtle measurement biases in telescopes like Planck and WMAP. Others propose more radical explanations, like the idea that our universe collided with another bubble universe in the multiverse, leaving a gravitational bruise on the CMB. The truth remains elusive, but one thing's certain. If this anomaly is real, it threatens to upend our assumption that the cosmos is fundamentally the same in all directions. Future missions like the Simons Observatory and CMB-S4 aim to settle the debate with unprecedented precision, mapping the CMB's fine details to distinguish signal from noise. Until then, the axis of evil stands as one of cosmology's most provocative puzzles, a whisper that the universe might not be as isotropic as we thought, and that dark energy's secrets could be written in the skewed shadows of the ancient sky. What if dark matter isn't just some exotic particle, but a quantum phenomenon woven into the fabric of reality itself? Quantum mechanics, the bizarre rulebook governing the subatomic world, might hold clues to this cosmic riddle. Take axions, for example. These ghostly particles were first proposed to solve a puzzle in quantum chromodynamics, the theory describing how quarks bind together. But here's the twist. Axions could also be dark matter floating through space in a cosmic quantum haze. Picture trillions of these ultralight particles, each 1 billion times lighter than an electron, forming a diffuse wave that permeates every galaxy. Their quantum nature means they wouldn't behave like discrete bullets but as ripples in an invisible ocean, a Bose-Einstein condensate stretched across the universe. A Bose-Einstein condensate is a state of matter where particles lose their individuality and merge into a single quantum entity, like a crowd moving in perfect unison. If dark matter exists in this form, it could explain why it doesn't clump as tightly as cold dark matter predicts. Instead of forming dense cores at galaxy centers, this quantum dark matter would spread out, smoothing the sharp edges we expect from simulations. This might solve the cusp core problem, where galaxies mysteriously lack the dense dark matter peaks models anticipate. It's as if dark matter is playing by quantum rules, refusing to be pinned down to a single location. String theory takes this quantum connection even further. In its tangled web of extra dimensions, axions could emerge as vibrations of cosmic strings, filaments of energy left over from the Big Bang. These strings might have stretched across the early universe, seeding axions in their wake. If true, dark matter wouldn't just be a passive ingredient in the cosmos, it'd be a relic of higher dimensional physics, a shadow cast by the universe's most fundamental structures. The implications are staggering. Detecting axions wouldn't just reveal dark matter. It could crack open the door to string theory itself, but the quantum dark matter connection doesn't end there. Some theories propose that dark matter could interact through a dark force, a hidden version of electromagnetism operating in a parallel quantum realm. Just as photons mediate light in our world, dark photons might govern interactions in the dark sector, creating complex structures invisible to us. This could explain why dark matter seems to clump differently at various scales, defying simple models. It's like discovering an entire shadow universe with its own quantum rules, silently shaping the cosmos alongside ours. The challenge: quantum effects are notoriously delicate, vanishing in the macroscopic world. To test these ideas, scientists are turning to ultra-precise experiments. Devices like Abracadabra and the Action Dark Matter experiment use powerful magnetic fields to coax actions into revealing themselves, converting their quantum whispers into detectable signals. Meanwhile, observations of neutron stars where extreme gravity might concentrate dark matter could reveal anomalies hinting at quantum behavior. Whether actions, Bose-Einstein condensates, or something stranger, the quantum dark matter link forces us to rethink the boundaries of physics. If proven, it would mean the universe's largest structures are governed by the tiniest rules, a cosmos where the quantum and the cosmic are inextricably entwined. And that's a mystery worth unraveling. The universe isn't just expanding, it might be dragging everything in it toward something we can't see. This bizarre phenomenon, called dark flow, was discovered when astronomers noticed hundreds of galaxy clusters streaming through space at breakneck speeds, all in the same direction, as if pulled by a cosmic magnet. The motion defies expectations. After all, the universe's expansion should scatter galaxies evenly in all directions, like raisins in rising bread dough. But these clusters are racing toward a single point beyond the edge of the observable cosmos, hinting at a gravitational anomaly so vast it could rewrite our understanding of reality. The first clues emerged from studies of the cosmic microwave background, the afterglow of the Big Bang. When scientists mapped tiny temperature fluctuations in this ancient light, they detected a subtle Doppler shift, a sign that galaxy clusters were moving collectively at nearly 2 million miles per hour. That's fast enough to cross the Milky Way in just a few 100 million years. Even stranger, the flow aligns roughly with a patch of sky near the constellations Centaurus and Vela, a region with no known supercluster or mass concentration powerful enough to explain the tug. It's as if the universe has a hidden current pulling galaxies toward an unseen horizon. One radical explanation: the gravitational influence of structures beyond our cosmic horizon. The observable universe is limited by the distance light has traveled since the Big Bang, about 93 billion light-years in diameter. But what lies beyond? If there's an enormous concentration of mass out there, a supercluster, or a vast, uneven distribution of matter left over from the universe's birth, its gravity could be warping spacetime enough to yank our entire neighborhood toward it. Think of it like standing on a beach, feeling the ocean's tide pull at your feet, even though you can't see the moon responsible for the force. Critics argue dark flow could be an illusion, a statistical fluke magnified by measurement errors or local peculiar velocities. Some suggest the motion might stem from incomplete corrections for the Milky Way's own movement, or from asymmetries in the cosmic microwave background that haven't been fully accounted for. Yet multiple independent studies, including data from the Planck satellite, have confirmed the anomaly persists even after painstakingly removing potential biases. The signal isn't just noise, it's a real, puzzling drift that refuses to vanish. If dark flow is genuine, the implications are staggering. It could mean our universe is far less uniform than the cosmological principle assumes, that on the grandest scales, matter isn't evenly distributed after all. Perhaps the Big Bang didn't unfold symmetrically, leaving behind colossal density variations that still tug at galaxies today. Or worse, it might hint that our cosmic neighborhood is caught in the gravitational wake of another universe entirely, a neighboring bubble in the multiverse exerting its invisible influence. For now, dark flow remains one of cosmology's most contentious mysteries, Upcoming galaxy surveys and deeper SIMB analyses could either solidify the case or reveal hidden systematic errors. But whether it's a flaw in our models or a window into the unseeable, one thing's clear: the universe still holds currents we're only beginning to navigate, and they might be pulling us toward answers we're not yet ready to understand. At the heart of dark energy's mystery lies a deceptively simple symbol, W. This single letter, representing the equation of state, encapsulates the entire identity crisis of the universe's most enigmatic force. It's nothing more than a ratio the pressure dark energy exerts divided by its energy density. Yet its value could reveal whether we're dealing with Einstein's static cosmological constant or something far more dynamic. Picture W as a cosmic dial, turn it to -1, and you've got lambda, the unchanging vacuum energy woven into space itself. But nudge it even slightly, and you enter the realm of quintessence, where dark energy morphs and evolves over time, potentially rewriting the universe's fate. The stakes of measuring W couldn't be higher. If dark energy is truly lambda, then W equals exactly -1, a fixed value that means the universe will expand forever at an ever-increasing rate, galaxies vanishing over the horizon until only cold emptiness remains. But if observations show W deviating from that magic number, even by a fraction, everything changes. A value greater than -1 suggests dark energy weakens over time, possibly allowing gravity to regain dominance in the distant future. Less than -1, that's the phantom energy scenario, where the universe careens toward a catastrophic big rip. The difference between these outcomes hinges on minuscule variations in W measurements so precise they push our telescopes to their limits. Why is pinning down W so maddeningly difficult? Blame the universe's subtlety. Dark energy's pressure isn't something you can measure directly like temperature or brightness. Instead, scientists resort to cosmic detective work, tracking how the expansion rate has changed over billions of years. Supernovae serve as mile markers, their redshifts revealing how much space stretched during their light's journey to Earth. Baryon acoustic oscillations, frozen ripples in the distribution of galaxies, act as a cosmic ruler, stretching over time in ways that betray dark energy's push. Even the growth of galaxy clusters, stunted by dark energy's repulsion, offers clues. Each method has its own systematic uncertainties, like a clock that's slightly fast or slow, and getting them to agree is cosmology's version of herding cats. The plot thickens when you consider that W might not even be constant. Some quintessence models propose it fluctuates across space or time, meaning today's gentle acceleration could become tomorrow's violent surge. Imagine the universe as an elevator with a faulty control panel, sometimes rising smoothly, sometimes lurching unpredictably. This volatility would leave fingerprints in the large-scale structure of the cosmos, subtle wrinkles that experiments like the dark energy spectroscopic instrument are now hunting. Current measurements hover tantalizingly close to -1, but with error bars just wide enough to keep the quintessence dream alive. The latest data from Planck and the Dark Energy Survey suggest W equals approximately -0.95 plus or minus 0.05, a whisper away from lambda, but not quite a definitive confirmation. It's like trying to discern whether a distant light is a stationary star or a slowly drifting satellite with the naked eye. The next generation of observatories, like the Euclid Space Telescope and the Vera Rubin Observatory, aim to shrink those uncertainties to a razor's edge. What makes this pursuit so electrifying isn't just the technical challenge, it's the philosophical weight. Determining W isn't just about fitting numbers into equations. It's about answering whether the universe is governed by a simple, elegant constant or a capricious, evolving force. One path leads to a predictable, if desolate, future. The other opens doors to cosmic upheavals we've barely begun to imagine. And somewhere in the interplay of pressure and density, in the delicate balance of a single parameter, lies the truth about how our story ends, or whether it ends at all. One of the most persistent headaches in modern cosmology isn't something vast, it's what's conspicuously absent. According to supercomputer simulations, our Milky Way should be surrounded by thousands of dwarf galaxies, tiny cosmic satellites held in orbit by dark matter's gravitational grip. Yet when astronomers count them, the numbers fall devastatingly short. We've found barely a few dozen of these faint, wispy companions, leaving a glaring mismatch known as the missing satellites problem. It's as if we've been handed a cosmic recipe predicting a feast, only to open the oven and find half the dishes missing. The roots of this discrepancy lie in how dark matter shapes the universe. Simulations like Via Lactea and Elvis model the aftermath of the Big Bang, tracking how dark matter clumps into halos that act as gravitational traps for ordinary matter. These halos come in all sizes, and the smallest ones, theorists argue, should have pulled in enough gas to ignite star formation, becoming dwarf galaxies. Think of it like rainfall filling countless puddles across a landscape, but observations show a far drier picture. The puddles either never formed or they evaporated before we could spot them. Enter baryonic feedback, a fancy term for the messy, explosive influence of ordinary matter. Gas isn't just passive fodder for galaxy formation, it pushes back. When stars are born, they blast powerful winds. When massive stars die, they explode as supernova, their shockwaves heating surrounding gas and flinging it outward. In small dwarf galaxies where gravity's grip is weak, these processes can be catastrophic. A single stellar explosion might eject all the star-forming fuel, leaving the galaxy stunted or even dark. It's like trying to light a campfire in a hurricane. The flames keep getting snuffed out before they can catch. This idea gained traction with discoveries like ultra-faint dwarfs, galaxies so feeble they're barely detectable. These cosmic afterthoughts are exactly what feedback models predict, systems where star formation sputtered early, leaving behind a ghostly halo of dark matter with almost no stars. Meanwhile, some simulations now incorporate these baryonic effects, showing how supernova and black hole activity can quench small galaxies, leaving the majority of dark matter halos empty. The result, a universe where dwarf galaxies are rare not because dark matter failed, but because ordinary matter was too unruly to cooperate, but not everyone's convinced. Alternative theories suggest we might just be bad at spotting dwarfs, that telescopes have missed a hidden population of ultra-diffuse galaxies, camouflaged against the night sky. Others propose that dark matter is warmer than we thought, its particles moving fast enough to smooth out the smallest halos before galaxies can form. The truth might lie somewhere in between, a combination of baryonic tantrums and observational limits, with room left for physics we haven't yet imagined. As telescopes like Vera Rubin and JWST peer deeper into the Milky Way's backyard, they're uncovering fainter dwarfs than ever before, testing whether feedback alone can explain the gap or if darker, stranger forces are at play. Either way, the missing satellites problem isn't just a census discrepancy, it's a stress test for our entire understanding of how galaxies, both great and small, are born from the dark. Why does dark matter outnumber ordinary matter by a staggering 5-to-1? The universe seems to have a bizarre preference for the invisible, leaving us along with all the stars, planets, and galaxies as cosmic afterthoughts in a sea of shadow. This lopsided ratio isn't just a curiosity, it's a screaming clue about the universe's earliest moments, hinting at a primordial imbalance baked into reality itself. To unravel this, we need to rewind to the first fractions of a second after the Big Bang, when particles and antiparticles were locked in a frantic dance of creation and annihilation. Consider baryogenesis, the process that gave rise to the tiny excess of matter over antimatter in our universe. For every billion particles of antimatter, there were 1,000,000,001 particles of matter, a microscopic asymmetry that allowed our universe to avoid complete self-destruction. What if dark matter owes its dominance to a similar twist of fate? Some theories propose a parallel process called asymmetric dark matter production, where dark particles were forged in greater numbers than their counterparts due to some fundamental bias in the laws of physics. Picture a cosmic coin toss that landed heavily on one side not just once, but enough times to flood the universe with dark matter's ghostly presence. The math is compelling. If dark matter particles were slightly heavier than their antiparticles, or if they interacted more weakly with the forces governing annihilation, they could have survived in far greater numbers than ordinary matter. While protons and electrons barely scraped by after matter-antimatter annihilation, dark matter might have coasted through this bottleneck untouched, stacking the deck in its favor. Some models even suggest that dark matter's asymmetry is directly tied to baryogenesis, that the same physics responsible for our existence also tipped the scales for dark matter. It's as if the universe settled on two separate accounting errors, one favoring us, the other favoring the unseen. But there's a catch. For this to work, dark matter must have some way of communicating with ordinary matter in the early universe, not through the forces we know, but perhaps via an undiscovered interaction. Imagine a hidden handshake between the two sectors, a fleeting exchange of energy or charge that skewed the numbers. Experiments like underground detectors and particle colliders are hunting for these phantom interactions, hoping to catch a glimpse of dark matter's secret influence on our world. The implications are profound. If dark matter's dominance stems from asymmetry, it would mean our universe's structure hinges on ancient, broken symmetries, tiny cracks in the laws of physics that allowed something to emerge from nothing. And if we ever prove this connection, it won't just solve the 5-to-1 riddle. It'll rewrite the story of how everything visible and invisible came to be. In the grand tapestry of the cosmic microwave background, there's a patch so bizarre it's been dubbed the CMB cold spot, a chilling anomaly where temperatures plummet far below the expected average. This cosmic cold front stretches nearly 1 billion light-years across, a vast and unexplained dip in the afterglow of the Big Bang. At first glance, it might seem like a statistical fluke, but the odds of such an extreme deviation occurring randomly are less than 1 in 50. That's like rolling a die 100 times and never landing on a 6 possible, but so unlikely it demands an explanation. One leading theory points to a supervoid, a staggering emptiness in the universe's structure where galaxies are eerily scarce. Picture a bubble so vast it could swallow thousands of Milky Ways, with so little matter inside that photons passing through lose energy, stretching to longer, cooler wavelengths as space itself expands within the void. This integrated Sachs-Wolf effect could theoretically explain the cold spot, but there's a catch. The void would need to be impossibly large, far exceeding predictions from standard cosmology. Even the most cavernous known voids, like the KBC void, can't fully account for the temperature drop. It's as if the universe carved out a hole far bigger than its tools should allow. Then there's the far more radical possibility. The cold spot might be a bruise from a collision with another universe, in the chaotic froth of eternal inflation. The theory that our universe is just one bubble in a vast multiverse. Such crashes could leave imprints on the CMB. Imagine two soap bubbles grazing each other. The boundary where they meet would ripple with energy. If our universe bumped into another bubble early in its history, the resulting shockwave could have chilled that patch of space, leaving behind a relic as cryptic as it is colossal. While speculative, this idea ties into broader questions about dark energy's role in shaping the cosmos. If dark energy drives eternal inflation, then these bubble collisions could be the fingerprints of its hidden architecture. Yet the mystery deepens when we consider dark energy's fingerprints. If the cold spot stems from a supervoid, its existence challenges our understanding of how dark energy shapes the universe's large-scale structure. Voids should grow over time as dark energy pushes galaxies apart, but the scale needed to explain the cold spot defies conventional models. Alternatively, if the spot is a multiverse relic, it could hint that dark energy's behavior isn't uniform, that its strength varies in ways we've yet to imagine. Either scenario forces us to confront gaps in our cosmic blueprint, gaps that might hide answers about why the universe accelerates as it does. Efforts to solve this puzzle are already underway. Telescopes like the Dark Energy Survey and the upcoming Euclid mission are mapping the distribution of galaxies around the cold spot, hunting for signs of a supervoid or structural quirks that could reveal dark energy's handiwork. Meanwhile, improved CMB measurements from projects like the Simons Observatory aim to scrutinize the spot's subtle textures, searching for patterns that might betray its origins. What makes the cold spot so electrifying isn't just its enigma, it's the doors it could open. Whether a cosmic void, a multiverse scar, or something even stranger, this anomaly reminds us that the universe's shadows still hold secrets. And in those secrets might lie the keys to dark energy's true nature and the fate of everything we know. Deep in the X-ray glow of distant galaxy clusters, a whisper of energy at precisely 3.5 kiloelectron-volts has ignited one of the most heated debates in modern astrophysics. First spotted in 2014 by two separate teams analyzing data from the European Space Agency's XMM Newton telescope, this faint emission line appears nowhere in the known catalogue of atomic transitions. Its presence defies conventional astrophysics unless, as some scientists daringly suggest, it's the radioactive signature of dark matter unraveling itself in the voids between stars. The theory hinges on sterile neutrinos, hypothetical particles that could bridge the gap between dark matter's gravitational grip and its invisible nature. Unlike their ordinary neutrino cousins, which flit through matter almost unnoticed, sterile neutrinos would interact solely via gravity, making them perfect dark matter candidates. If these particles exist, they'd occasionally decay, emitting X-rays at an energy determined by their mass, and 3.5 keV lands squarely in the predicted range. It's like catching a murderer by the unique heat signature of their getaway car, except in this case, the suspect is a particle that might not even exist. But the plot thickens with contradictions. Follow-up observations have been a roller coaster of confirmation and refutation. NASA's Chandra X-ray Observatory failed to detect the line in the same clusters where XMM Newton saw it, sparking accusations of instrumental artifacts or background noise. Then came studies of the Milky Way center, where dark matter should be densest. Some groups reported the signal, others found nothing. The statistical significance wobbles like a house of cards, with some analyses claiming 5 sigma confidence, the gold standard for discovery, while others dismiss it as a fluke no more meaningful than static on a radio. Critics argue the line could stem from mundane sources, potassium ions in hot plasma or sulfur atoms undergoing exotic transitions. Yet the spatial distribution of the signal adds another layer of intrigue. In the Perseus cluster, the 3.5 keV line appears stronger in regions where dark matter is thought to dominate, not where ordinary matter glows brightest. It's as if the X-rays trace an invisible skeleton lurking behind the luminous gas, a shadowy structure only decaying dark matter could explain. The stakes are astronomical. If this line is real, it would be the first direct detection of dark matter's particle identity, crowning sterile neutrinos as the leading candidate overnight. Laboratories worldwide would pivot to test this hypothesis, racing to recreate the decay in particle accelerators or underground detectors. But if it's an illusion, it's a costly 1 year of telescope time and theoretical effort spent chasing a cosmic mirage. For now, the 3.5 keV line remains suspended in Schrödinger's paradox, simultaneously a breakthrough and a blunder until future observatories like Athena or XRISM settle the debate. Whether it fades into obscurity or reshapes our understanding of the universe's hidden bulk, one lesson is clear: even the faintest tremors in our data can shake the foundations of cosmology. In the quest to unravel dark energy's mysteries, string theory has thrown a curveball, one that could rewrite the rules of cosmic acceleration. Known as the swampland conjecture, this bold idea suggests that certain theoretical landscapes in physics are unstable, like building a house on quicksand. Among its most startling claims, dark energy can't be a simple, unchanging cosmological constant. It must be dynamic, shifting over time or space. If true, this would force us to abandon Einstein's static lambda and confront a universe where dark energy is far stranger than we ever imagined. At its core, the swampland conjecture is about viability. String theory, with its intricate web of extra dimensions and vibrating strings, predicts an almost infinite number of possible universes, each with different physical laws. But not all these universes are mathematically consistent. Some collapse under their own contradictions, landing in the so-called swampland. The conjecture's criteria act like a cosmic bouncer, separating workable theories from doomed ones. One key rule: dark energy's equation of state can't be perfectly constant. Its value, W, must either evolve over time or vary across space, disqualifying lambda as we know it. Think of it like a river that can't flow at a steady pace. It must either speed up, slow down, or change course. This idea gained traction when physicists noticed a bizarre tension. While the cosmological constant fits most observations, it's too perfect. Quantum field theory predicts a vacuum energy density absurdly larger than what we observe, a discrepancy of 120 orders of magnitude. The swampland conjecture offers a way out, proposing that lambda's apparent stability is an illusion, a temporary snapshot of a deeper, evolving force. It's like realizing the constant hum of an engine is actually the sum of many shifting vibrations. Observational clues add fuel to the fire. The Hubble tension, the mismatch in expansion rate measurements, could hint at dark energy's dynamism, as could anomalies in large-scale structure. If dark energy's strength varied slightly across cosmic epochs, it might explain why local supernovas suggest faster expansion than the early universe's CMB predicts. Even the CMB cold spot and cosmic voids, with their strange gravitational footprints, might fit into this puzzle. The swampland conjecture turns these anomalies from nuisances into potential evidence, reframing them as ripples in dark energy's fabric. Yet the conjecture remains contentious. Critics argue it's too vague, a moving target that retrofits itself to any new observation. Others point out that current data still favors lambda, with W hovering stubbornly close to -1. But proponents counter that precision measurements, like those from the upcoming Euclid telescope, could finally reveal subtle deviations, tiny wiggles in W that betray dark energy's true dynamic nature. Whether the swampland conjecture holds up or not, its real power lies in shaking our assumptions. It forces us to ask, is dark energy's simplicity a clue or a coincidence? Are we mistaking a single frame for the entire film? As experiments push deeper into the cosmos's shadows, we might find that the universe's acceleration isn't just a feature of space, but a story still unfolding. Long before galaxies or stars flickered into existence, dark matter may have taken shape in the furnace of the early universe, a cosmic relic forged in the first chaotic microseconds after the Big Bang. Picture a universe so hot and dense that particles collided frenetically, constantly annihilating and re-emerging from the seething energy of creation. In this primordial chaos, dark matter could have been born through a process called thermal freeze-out, a dramatic parting of ways when the expanding cosmos cooled just enough to slam the door on particle collisions forever. Here's how it might have happened. In the earliest moments, dark matter particles, whether WIMP, axions, or something else, were in thermal equilibrium, constantly interacting with the soup of quarks, gluons, and other particles. But as the universe expanded and cooled, there came a critical moment when the temperature dropped below the energy needed for dark matter to keep colliding with ordinary particles. Like dancers leaving a ballroom as the music fades, these particles suddenly stopped interacting, freezing out of the cosmic plasma and drifting into the shadows. Their abundance became locked in, a snapshot of the universe's conditions in that fleeting instant. The staggering implication, the dark matter we detect today, its density, its distribution, could be a fossil of that exact moment preserved across billions of years. Yet freeze-out isn't the only origin story. Another compelling theory ties dark matter's birth to the inflationary epoch, that mind-bending fraction of a second when the universe expanded exponentially, stretching quantum fluctuations into cosmic-scale wrinkles. These fluctuations, tiny variations in density, could have seeded dark matter's eventual clumping, much like microscopic ripples growing into towering waves. Some models even suggest that dark matter particles were directly spawned by inflation's energy, condensing out of the vacuum like dew forming on a cold surface. If true, dark matter wouldn't just be a passive remnant, it would be an active signature of the universe's most explosive growth spurt. Enter particle colliders, humanity's time machines for probing these ancient mysteries. By smashing protons together at near light speeds, machines like the Large Hadron Collider recreate conditions not seen since the universe's first trillionth of a second. The hope that a collision might briefly conjure dark matter particles into existence, leaving behind a telltale energy imbalance in the detectors. While no direct detection has been confirmed, these experiments have ruthlessly narrowed the possibilities, ruling out entire classes of hypothetical particles. Other approaches, like hunting for axions with ultra-sensitive magnetic resonators, aim to catch dark matter's faint whispers, particles so elusive they've slipped through every other net. But the most tantalizing clues might come from the cosmos itself. The cosmic microwave background's faint imprints and the intricate web of galaxy clusters serve as a fossil record, encoding dark matter's primordial properties. If we can decode these patterns, whether through next-generation telescopes or underground detectors, we might finally glimpse the universe's shadowy beginnings, revealing not just what dark matter is, but how it shaped everything that followed. What if dark matter isn't made of exotic particles at all, but of black holes lurking in the cosmic shadows? This audacious idea, once relegated to the fringes of cosmology, has clawed its way back into serious consideration. Primordial black holes, hypothetical relics forged in the universe's first chaotic seconds, could solve two mysteries at once: the nature of dark matter and the origins of the supermassive giants anchoring galaxies today. Imagine a universe where black holes didn't form from dying stars but were born in the furnace of the Big Bang itself, their seeds sown by quantum fluctuations or phase transitions in the seething early cosmos. These ancient objects, ranging from the mass of a mountain to thousands of suns, would be virtually invisible, yet their gravitational grip could explain every puzzle dark matter presents. The appeal lies in simplicity. Unlike WIMP or axions, black holes don't require undiscovered physics. They're made of ordinary spacetime, warped beyond recognition. If enough primordial black holes formed, they could permeate galaxies in vast, unseen swarms, tugging on stars and bending light exactly as dark matter does. Some theories even suggest these black holes could be the missing link in galaxy formation, their gravity providing the scaffolding for the first stars. And there's a tantalizing symmetry here. Just as dark matter dominates galaxies' outer halos, supermassive black holes rule their cores. Could they be opposite ends of the same cosmic spectrum? But the universe has a way of dashing elegant ideas. Microlensing surveys searches for the telltale brightening of stars when unseen masses pass in front have placed tight constraints on primordial black holes. Projects like OGLE and HSC have scanned millions of stars for years, expecting frequent flashes if black holes were common. Instead, they've found far fewer events than needed to account for all dark matter. The verdict, black holes between the mass of the Moon and 1,000 suns, can't be more than a fraction of the universe's missing mass. It's as if we've ruled out every hiding place in a cosmic game of hide and seek, leaving only the tiniest cracks for these objects to slip through. Yet the story isn't over. Black holes lighter than an asteroid or heavier than 1,000 suns remain viable candidates escaping microlensing's net. Some theorists propose planet-mass primordial black holes, so small they evaporate before detection, yet collectively, their gravity could still bind galaxies. Others focus on intermediate mass black holes, those elusive entities weighing thousands of solar masses, which could hide in galactic halos without triggering lensing surveys. The recent LIGO detections of surprisingly hefty black hole mergers have even fueled speculation. Could these be ancient remnants of dark matter's hidden population? The most radical twist, primordial black holes might not just be dark matter, they could create it. A black hole's event horizon isn't a one-way street. Quantum effects cause them to emit particles, a process called Hawking radiation. Microscopic black holes would evaporate explosively, but larger ones could leak dark particles into the cosmos, seeding the very halos they inhabit. It's a cosmic feedback loop where gravity and quantum mechanics conspire to shape the universe twice over, first with their mass, then with their decay. Whether primordial black holes solve the dark matter riddle or fade into cosmic obscurity, their resurgence proves one thing: sometimes the most compelling answers aren't new particles hiding in labs, but ancient monsters we've overlooked in plain sight. And as telescopes peer deeper into the voids and gravitational wave detectors tune into the universe's faintest tremors, we might yet discover that the darkest stuff in existence isn't strange, just supremely, tragically familiar. One of the most baffling quirks of our universe isn't just that dark energy exists, it's when it decided to take the wheel. Picture this: for billions of years after the Big Bang, gravity dominated the cosmic scene, patiently gathering matter into galaxies and clusters. Then, right around the time life could have first flickered into existence on Earth, dark energy surged forward, not too early, not too late, just as the universe hit a sweet spot where galaxies had finished assembling but hadn't yet been ripped apart by accelerating expansion. This eerie timing isn't just convenient, it's cosmically suspicious. How did dark energies rise to power, now making up roughly 70% of the universe's energy budget, coincide so perfectly with the golden age of cosmic structure? This puzzle is called the coincidence problem, and it cuts to the heart of why dark energy feels less like a natural phenomenon and more like a cosmic plot twist. If dark energy's density was slightly higher, it would have overwhelmed gravity before galaxies could form, leaving the universe a featureless void. Slightly lower, and gravity would have kept dominance indefinitely, causing a catastrophic collapse long before life could emerge. Instead, we exist in a razor-thin sliver of cosmic history where these two titans, dark energies push and gravities pull, briefly balance each other. The odds of this happening by chance are astronomically low, like a pencil balancing on its tip for billions of years without toppling. Some theorists argue this isn't coincidence at all, but evidence of a deeper principle, a fundamental link between dark energy and the conditions for complexity. One radical idea, inspired by the anthropic principle, suggests that universes with different dark energy strengths exist in a vast multiverse, and we simply inhabit the rare one where the numbers allowed galaxies and thus observers to form. It's like a cosmic version of survivorship bias. Of course, we find ourselves in a universe where the timing works, because all other possibilities lack the ingredients for life to even notice the mismatch. Others propose that dark energy isn't a static force but a dynamic field that somehow knows when to activate based on the universe's structure. In quintessence models, dark energy's strength could be tied to the average density of matter, meaning its rise wasn't random but triggered by the natural thinning of matter as galaxies spread apart. Imagine a seesaw. As matter dilutes with expansion, dark energy's influence grows to counterbalance it. This would make the coincidence an illusion, the inevitable outcome of a hidden feedback loop woven into spacetime itself. Yet even these explanations leave gaps. If dark energy is dynamic, why does its observed behavior so precisely mimic a cosmological constant, a static energy embedded in space? And if we're in a multiverse, why does our universe's dark energy density hover just barely above the threshold needed for galaxy formation, rather than being comfortably higher? These wrinkles hint that the coincidence problem might be pointing toward physics beyond our current models, perhaps a universe where dark energy and matter communicate through undiscovered forces, or where the very fabric of reality operates differently on cosmic scales. The stakes here are more than philosophical. If dark energy's timing isn't accidental, it implies the universe has an underlying unity we've yet to grasp, a set of rules that synchronize its largest components like gears in a clock. Upcoming telescopes like the Vera Rubin Observatory and Euclid could shed light on this by measuring whether dark energy's strength has changed over time, testing whether its rise was pre-programmed or a fluke. Until then, the coincidence problem remains cosmology's most tantalizing itch, a reminder that the universe's greatest mysteries might not lie in the darkness we can't see, but in the patterns we've yet to understand. What if our universe's baffling dark energy value isn't a cosmic accident, but just one page in an infinite library of possibilities? Multiverse theories propose a staggering vision. Our universe might be a single bubble floating in an endless cosmic foam, each bubble with its own unique laws of physics. In some, dark energy's repulsive force could be so strong that space tears apart before stars ignite. In others, it might be too weak to overcome gravity, collapsing everything back into a primordial crunch. Yet here we are, in a universe where dark energy's strength is bizarrely fine-tuned, just enough to allow galaxies to form, but not so much that they're instantly vaporized. This razor-thin balance isn't just luck. It might be the inevitable consequence of an unimaginably vast multiverse where only life-friendly bubbles can ever be observed. The anthropic principle cuts through this cosmic coincidence like Occam's razor. Imagine a fisherman casting nets into the ocean. He'll only ever catch fish that can survive in the mesh size he's using, not because the ocean lacks other fish, but because his filter selects for certain traits. Similarly, if countless universes bubble into existence with random dark energy values, only those where the number allows for galaxies, and thus observers, will ever have someone around to wonder why the math works out so perfectly. Our universe's Goldilocks dark energy isn't special, it's survivable. This logic extends even to the cosmological constant problem. Quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than observed, a catastrophic mismatch unless most universes do have those lethal values, and we simply can't exist in them to complain. String theory's landscape adds fuel to this fire. With potential solutions numbering 10 to the power of 500, it suggests a vast cosmic lottery where every possible physical constant gets its turn. Some bubbles might have dark energy so weak that black holes dominate, while others expand so fast that matter never clumps. Our bubble hit the jackpot, a dark energy density of roughly 1 hydrogen atom per cubic meter, allowing just enough structure for complexity to emerge. The kicker, even slight deviations would render life impossible. Increase dark energy by a factor of 20, and galaxies never coalesce. Reduce it by half, and the universe collapses before life gets a foothold. Yet the multiverse explanation leaves some scientists uneasy. Without observable proof of other universes, critics argue it risks being unfalsifiable, a metaphysical shrug rather than testable science. Others counter that certain signatures, like anomalous cold spots in the cosmic microwave background, could hint at collisions with neighboring bubbles. Future telescopes might even uncover statistical wrinkles in large-scale structure that betray our universe's place in a wider cosmic tapestry. Whether these searches pan out or not, the multiverse framework forces us to confront a humbling truth. The laws we consider fundamental might be nothing more than local bylaws in an infinite cosmic metropolis, and dark energy's whisper might be the echo of countless unseen worlds. The race to unmask dark matter and dark energy is entering its most thrilling chapter yet, with a new generation of telescopes, detectors, and particle colliders poised to revolutionize our understanding. Leading the charge is ESA's Euclid spacecraft, a cosmic cartographer designed to map the universe's hidden skeleton in unprecedented detail. Unlike Hubble's deep but narrow gaze, Euclid will survey a third of the sky, charting the positions and shapes of billions of galaxies. Its secret weapon, measuring how dark matter's gravity distorts those galaxies, a phenomenon called weak gravitational lensing. With such precision, it could reveal whether dark energy's strength has changed over time. Imagine photographing a vast field of candles to see if their flames flicker in unison. Euclid's lensing maps will expose whether dark energy burns steadily or dances unpredictably across cosmic history. Meanwhile, NASA's Nancy Grace Roman telescope, set to launch in the mid-2020s, will tackle the mystery from another angle. Dubbed the Mother of Hubble, this observatory pairs a field of view 100 times wider than Hubble's with infrared vision that pierces through cosmic dust. Roman's primary mission: create a 3D movie of the universe's expansion by capturing millions of supernova and galaxy clusters. But its real dark matter sleuthing comes from an ingenious trick observing how light bends around invisible mass concentrations in a technique called microlensing. If primordial black holes lurk in galactic halos, Roman could spot their fleeting shadows as they pass in front of distant stars. It's like setting up a billion security cameras across the Milky Way, each waiting to catch dark matter's shadow in motion. On the ground, CERN Large Hadron Collider is preparing for upgrades that could blast open new frontiers in particle physics. The high-luminosity LHC, set to switch on in 2029, will collide protons at 10 times today's rate, creating a firestorm of data where rare dark matter particles might briefly flicker into existence. While WIMPs have eluded detection so far, these supercharged collisions could produce dark sector particles that interact through unknown forces. Picture smashing clocks together at nearly light speed, hoping the debris reveals gears from a parallel timekeeping system, one governed by rules we've yet to imagine. But the most revolutionary tool might be the Vera Rubin Observatory's legacy survey of space and time. Starting in 2025, this Chilean behemoth will scan the entire southern sky every few nights for a decade, creating the most comprehensive time-lapse of the universe ever made. Its 32 billion pixel camera could catch dwarf galaxies so faint they've been invisible until now, testing whether the missing satellite's problem stems from observation limits or flawed dark matter theory. And by tracking how cosmic voids expand, it may uncover whether dark energies push varies across space, a clue that could support radical ideas like quintessence. Underground, experiments like LUX Zeppelin and Darwin are reaching new levels of sensitivity in the hunt for WIMP. These detectors, buried beneath miles of rock to shield from cosmic noise, now use liquid xenon so pure it can sense a single photon from a potential dark matter collision. Meanwhile, action hunters like ADMX and Haystack are tuning their dark matter radios, ultra-sensitive magnetic resonators, to scan for the hypothetical particles' faint signals across a range of masses. It's like searching for a station on a cosmic dial, not knowing which frequency might crackle with the voice of an invisible universe. The coming decade promises more than incremental progress. It's an all-out assault on the unknown. From neutrino observatories like IceCube tracking dark matter annihilation in the sun to atomic clocks so precise they could detect fluctuations in fundamental constants driven by dark energy, each experiment offers a new lens on the cosmos' darkest secrets. Whether through direct detection, gravitational fingerprints, or particle collisions, one thing's certain: the next chapter in this story won't just fill gaps in our knowledge. It may rewrite the book entirely. We've journeyed through 30 of the most perplexing enigmas surrounding dark matter and dark energy, from the ghostly tug of unseen halos to the universe's runaway expansion, from the bizarre alignments in the cosmic microwave background to the whispers of 3.5 keVx rays that might, or might not, be dark matter's dying breath. Each mystery peels back another layer of our cosmic ignorance, revealing just how little we truly understand about the forces shaping reality. Think about it: 95% of the universe's content is missing from our textbooks, and the remaining 5%, everything we can see, touch, and study, might be nothing more than flotsam adrift on an invisible sea. What makes these puzzles so electrifying isn't just their scale, but their stakes. Crack the code of dark matter, and you might unlock entirely new branches of particle physics, rewriting the standard model in the process. Decipher dark energy's secrets, and you could reveal whether the cosmos will end in ice or fire, or something far stranger. Even the wildest theories, from primordial black holes to multiverse collisions, remind us that the universe is under no obligation to make sense to us. Yet, this isn't just astronomy's problem, it's humanity's. Every unexplained rotation curve, every anomalous gamma-ray signal, every void that defies expectation is a thread in a tapestry we're still weaving together. The answers won't come from one telescope or lab, but from countless minds daring to ask, what if we're wrong? That's the thrill of science, the moment a single observation overturns decades of assumptions, and the cosmos whispers back with a truth more fantastic than fiction. So as we stand on the edge of discovery, peering into the dark, here's the real question: which of these mysteries sparks your imagination? Is it the phantom galaxies missing their dark matter, or the void stretching like cosmic yawns? The eerie synchrony of the axis of evil, or the rogue black holes that might lurk in the shadows? Drop your favorite in the comments, because the next breakthrough might not come from a lab, but from a conversation like this one. After all, the universe's greatest secrets don't just belong to scientists, they belong to anyone who's ever looked up at the night sky and wondered what's out there.